Okay, now that you guys have watched these videos with all the different atomic theories, I want to put them all together so hopefully it makes sense in the progression from the oldest to the newest. Okay, now you've watched the videos, you've taken the notes, but I'm going to give you some details that you need to know that maybe you didn't catch from the video, or greater detail to help you really understand. Okay, we haven't always known about the atom. The idea of the atom came about really back here centuries ago. These two guys were having an intellectual debate with one another. You see, people used to explain the world by logic. They would explain things, and I've done this in video before, but they had these weird thoughts like frogs came from mud, because the logic was everywhere you saw a frog, it was near mud. So they thought that you just pack mud together, you get a frog. And they thought that maggots came from rotting meat, and it was all this logic. And finally, they would come about experiments. But during this time, these two very smart individuals are having a debate on what makes the universe. They're looking at the world saying, what makes everything? And Democritus said, you know what, I imagine that if you broke things to the smallest part, you would get to this thing called the atomos, or the atom. Okay, and you can tell that that's where it comes from. That's a Greek word for what we have as atom now. And Aristotle said, well, I really don't believe that. Like if you take a loaf of bread and you tear it in half, you have a half a loaf of bread, but it's still bread. Tear it in half, it's still bread. You could break a piece. You could break it down forever. His logic was you would never reach an individual particle, because if you had something there, if anything's there, you should be able to break it in half and then break it in half again. And so they called that matter being continuous. Now, for you and I, one of these guys, we've really heard that name before, and that's Aristotle. And everybody in that time believed Aristotle. And so that idea of the atom being that there wasn't an atom, but that matter was continuous, lasted for centuries. Until we get into like the early 1700s, the 1800s, and this guy named Dalton comes around and says, we're believing some really, really weird stuff. Frogs come from mud, maggots come from rotting meat. That didn't make sense. And he said, prove it. And they started doing experiments. And finally, the idea of the atom comes along. And Dalton's the main guy that says, I think I know what the atom is. Okay? And basically he said the atoms were tiny, solid, indivisible. Now notice that word's not invisible. Indivisible means you can't break it down. So he saw the atom as hard and solid, okay? And indivisible spheres. He said the only difference between an atom on the periodic table of carbon and uranium is that the uranium's much larger. It's a lot heavier. So it's the idea of having a ball, okay? A golf ball compared to a marble. Both balls are spheres. One's just heavier than the other. Then you take a basketball, way bigger. So he basically said everything on the periodic table that we've been looking at is basically the only difference between all of them. They're all tiny solid spheres. The only difference is they weigh different. And if you find one atom in one part of the world, let's say it's gold here in America, and you find a gold atom in Australia, they weigh exactly the same. And it's very logical for the time. But we know that's inaccurate. And so as they start moving through technology, they start finding things. The study of electricity comes out. They first discovered electricity. And there's this guy by the name of Crook. And in the video, you saw them show you Crook's tube. Okay? I'm going to draw a very primitive version so you can understand what he did more than what you saw in the video. He took a really long glass tube, sort of like a neon sign. Okay? And what he did was he had a wire hanging out of it. This would be a great thing to write in your notes to help you remember. And he ran it to a battery. Many of you have probably seen the batteries that have the two big terminals on the top of it. And so he had a glass tube with a wire going to it. Okay? Matter of fact, it was called the Cathode Ray Tube. He called it the Cathode Ray Tube, or the CRT, Cathode Ray Tube. And basically, this would end up being the beginnings of where we get televisions, okay? He found that if you had a gas inside and you run electricity through it, what would happen is, in the middle of that, you would have a beam that jumped across there. And they'd never seen that before. Is it light? What is it? They started doing experiments on it. They didn't know what it was. And so one of the things that Crook tried was he put a magnet close to it. He put a positive magnet to it, and something really weird happened. Right there where he put the magnet, it bent toward it. What would that tell you? It has a charge, right? What charge is it? Okay? And Crook said that this beam had a negative, big word, charge. had a negative charge, but he didn't really know what it was going to be used for. Okay, all of that's Crook. Now you'll notice along the way that most of these science, there's two guys because they're going to work together. Okay, and that's all that Crook did. He made the cathode ray tube. He made the cathode ray tube. Okay, so he had a tube that had gas in it, and a wire ran down to a battery, and on that battery was a positive and a negative. And all of a sudden, this beam jumps through there. They do some experiments on it, and he found he could bend it with a magnet. That was cool. And that's all he found. Until this guy by the name of J.J. Thomson comes along. Okay, I'm going to put a star right here because J.J. Thomson, just like Dalton and just like these guys, are the main characters that you have to know. You have to know them all, but they're the main guys, and here's why. J.J. Thomson comes along, and he does something important. He's going to revise the cathode ray tube. Now, what does that mean? You can imagine that somebody along the way made a screwdriver. But a person that made the screwdriver is not the person that got credit for building the car. Even though screwdrivers are used to build them or work on them, the screwdriver didn't make the car. So here's the deal. Crook made the cathode ray tube. It's Thomson who figured out what it meant. Okay, so here's what happened. He looked at this cathode ray tube, and the one you see in the video is a very modern version of it. But he took the cathode ray tube and he wondered what was happening. So what he did was he revised it. He changed it. Okay, so here's what he did. He thought, I wonder what makes this. There's a wire. Okay, so wires are usually copper. So he said, I'm going to do something different. I'm going to make one with zinc wires. Okay, so he made zinc wires, plugged it all in, boop, got the same thing, negative charge. Then he made one with aluminum wires. Okay, and he made one with nickel, made out of nickel. Okay, the element nickel. And every time he got the same result. So is it the wire that's causing this to happen? No. So he said, okay, what else do we have? Well, we have glass that makes this tube. Now, there are different kinds of glass. Now, you know this. The windshield of your car is very different from the window of your house, which is very different from the glass that you drink out of. They're all different kinds of glasses. Okay, so the material of glass is made different ways. A beaker, graduated cylinder, all different types of glass. He changed all the types of glass. Did the experiment again, got the same result every time. So it wasn't the metals, it wasn't the glass. The only thing left is the gas inside. Instead of air inside, he did different things like he put neon in it, ran the electrical charge. He put argon into it. He put helium into it. And every time he ran the experiment, he got exactly the same results. And finally, he gets it. I know what's happening. You see, Crook said the beam had a negative charge. J.J. Thomson comes along and says, no, it's more than that. He said, very important statement, all matter has a negative charge. And he called it the electron. He gets credit for what we know as the electron. He says all matter has this negative part called the electron. How awesome is that? Now, what happens really in that time, in the middle 1800s, is science goes crazy. And here's why. If there's a negative part of it, there must be a positive part. Now, here's what happens for J.J. Thomson. J.J. Thomson would end up winning the Nobel Prize in physics for his work. Knowing that matter all has a negative charge in his experiment, all this stuff, he gets the Nobel Prize. Now, with the Nobel Prize, you may not know this, but the Nobel Prize, if you win that, there's money that comes with it, the prestige of it, the award that comes with it. You're the best in your area in the whole world that year. It's an amazing accomplishment. And so J.J. Thomson ends up winning the Nobel Prize for all of his work. And so what happens very quickly is automatically Dalton's not right anymore. The atom's not tiny, solid, or indivisible. There's something inside. Okay? So man, it's already changed from we think there are atoms to here's a really good idea of the atoms to it's changed. And so the science world asks, all right, J.J. Thomson, what does the atom look like if Dalton's wrong? And he said his theory is what is called the plum pudding theory. Now that's a really weird theory. See, he's from England, and they have this dessert. They're called plum pudding. And basically, it's sort of like oatmeal with raisins in it, except it's plums. It's a sweet dessert you would have. And so he basically said, I don't see the atom as tiny, hard, and solid. He said, here's what I see. I see the atom as a sphere that's positive with a bunch of negatives floating around inside. And when people in Europe heard plum pudding theory, they were like, oh, that makes complete sense. That's what the atom must look like. You have a positive sphere so think of it as a piece of watermelon. If you cut it open, all the red would be the positive and all the negatives would be the seeds of the watermelon. And it made very logical sense from everything that he saw. Now, for you and I, is that what the atom looks like? No, it's going to change. But this is the first real guess based on experiments. Crook made the device, but J.J. Thomson, who gets credit for the electron, revised it. He changed the metals, he changed the gas, he changed the glass, and got the same result every single time. And realized that all matter has this negative component called the electron. And then science goes crazy, because if there's a negative part, there's a positive part. And with that positive part is going to come all the money, the prestige, and all the stuff that comes along. But they're studying in electricity, and they can't find it. Where they're going to discover it is in a completely different place. Along comes a guy by the name of Becquerel. And you watch the video on Becquerel, and Becquerel was a scientist who accidentally discovered radioactivity. Remember, they showed you he had a ball of uranium and he put it in his desk drawer, wrapped up in paper. And he came back a couple of days. Imagine it's a Friday afternoon. He's been studying this substance called uranium. He doesn't know what it is. And matter of fact, they tell you in the video that it's kicking off these high-speed particles. And we know you don't want to be around radioactive things very long. It can make you very sick. But he had no idea. Couldn't feel it. Didn't know what was happening. So at the end of the day on a Friday, wraps up some paper, sticks it in a desk drawer. Comes back after the weekend and something crazy's happened. He had some film in the drawer. Now, many of you have seen the older cameras, not digital cameras, but a camera that actually has film in it. And it has to be developed in a dark room. And you've seen movies where they turn the red light on and they develop the film and they make pictures. And after that weekend, he noticed that on the film there were spots. Well, it was in a dark drawer. The only thing that exposes film is light. Every time you take a picture, it opens the shutter on the front, lets some light in, you get a picture. But there's no light in that dark drawer all weekend. And he realized there was something going from that uranium to that film, and it was developing it. And he discovered radioactivity. Okay? So we know that Becquerel, that's his name, he discovered radioactivity, and it was by accident. And along comes this very important character by the name of Rutherford. Okay? Rutherford comes along and does this crazy experiment. I'm going to get me a new pen real quick. He does this crazy experiment. I'm going to show you exactly, with my best drawing that I can, what he did. Rutherford did what was called the gold foil experiment. Now, in the video you watched, they talked about these high-speed particles called alpha particles. We started learning a whole lot about radioactivity after Becquerel discovered it. And so Rutherford said, well, if you have these high-speed particles that are coming out of substances, I wonder what they can do. So here's what he did. Now, I'm going to draw it like we're in a helicopter looking at it. Okay, so here's what he's going to do. Is he has a wall he built, and it's a fluorescent. And I would make sure that just like I'm writing this, that you're writing all this stuff down. He has a fluorescent screen. Now, what does fluorescent mean? Now, fluorescent's used in a lot of different ways in today's world. Let me show you. Okay? Some people will say that this highlighter is a fluorescent yellow. It just means like a bright yellow type thing. But that's not the fluorescent thing I'm talking about. You ever been in black light? Okay, and how things glow? Okay, when people's teeth really glow, their eyes really glow. If you have writing like this, it really glows in that, it really stands out. Okay, so he put a coating on this metal wall. So think of this wall sticking up like this. Okay, so it's a big wall. Okay, and what he's going to end up having on this end is he's going to have a lead box. Now, lead is the only thing radioactivity will not go through. So when you and I go to the doctor, or a better example is when we go to the dentist and we have x-rays taken on our teeth to make sure our teeth are okay. You ever notice they put all that film inside your mouth and they're like, I'll be right back, be real still. And they walk away and then they come back. They can't be around that x-rays and they lay that lead blanket on you to protect you from those x-rays. Okay, because lead is the densest metal we have on the periodic table. It doesn't let radioactivity go through it. And so he has a lead box, and inside here, he's going to have radioactive polonium, PO, on the periodic table. We're already learning our elements and symbols. And so Polonium, they knew, gave off alpha particles. Now, that's the Greek letter alpha. It's a type of particle that's sent off. So radioactivity, we'll learn here in a couple days, has alpha, beta, and gamma type of radiation, okay? And you'd be like, oh, gamma radiation, the Hulk. Okay, we'll talk about that when we get to radioactivity. But polonium gives off alpha particles, and he has this lead box and with these alpha particles in it. Notice I have a hole here. And so what's going to happen is, I'm going to make sure and fill this picture in right, is he has this screen like this. So think of it sort of like a corral standing up, and we're looking down on it. And as soon as he starts the experiment, what happens is he sees a spark. Boom, right there. Now, you've seen a spark before. That was weird. Oh, that's why that fluorescent screen worked. See, he had to do a whole lot of experiments, and what he found is when alpha particles hit this compound called zinc sulfide, and that's just its formula, zinc sulfide. You don't even have to know that name. I'm just telling you the whole story. But when an alpha particle hits a zinc sulfide, there's a spark. Now, I can't see those particles. The alpha particles are coming out, but they're coming out in such a manner that you can't see them. They're too tiny. Okay? And so what's actually happening is he can see a spark. And all of a sudden he sees spark, 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 spark. And you saw this in the video, and those particles were running out. And actually, they were showing you, but you couldn't see them with the naked eye, but you're seeing sparks there. So he's watching the experiment, and he thought, okay, what can I get these particles to do? So he set up what is called his gold foil experiment. He took a piece of gold and he put it right in front of the radioactive box, or that lead box that has radioactivity in it. Gold is very, very soft, so you can cut it very thin. So he's trying to cut it so thin that it was only a couple of atoms thick. And he's going to shoot at it. It's almost like taking a gun and you're going to shoot at a target. Okay? That's all he's doing. And so he starts the experiment again. And then all of a sudden he sees spark, spark, spark. What would that tell you? Yeah, it went right through it. He expected that. You see, if J.J. Thomson was right, with a positive sphere and a bunch of negatives in it, it's just like taking a gun with a bullet and shoot it through a piece of paper. It goes through that every time. And so he's watching spark, 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 and then something weird happens. He sees a spark right here, right there. What would that tell you? Well, it had to bounce, didn't it? It bounced off. So if something like this happened, that was crazy. That shouldn't happen, okay? And they even said in the video, it's as if you took a cannonball and tried to shoot it through a piece of tissue paper and it bounced back. That shouldn't happen. Why? There's nothing inside the atom that would make that happen. But did it happen all the time? No. Most of the sparks were happening out here. And he watched, and he watched, and he watched, and he watched, spark, 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 spark. And just every once in a while, he would have something bounce back. And so Rutherford came up with what he thought, okay, this can't be right. Plum pudding theory can't be right. And he said, here's what must be happening. He said, first of all, atoms are mostly empty space. Why? These particles flew right through it with no problem at all. Second thing he said, there must be a dense center in the atom. He called it the nucleus. He's given credit for that word. He said, all those particles that are in the atom, those electrons, and this positive part we're looking for, they must be, all those positive parts must be in the middle called the nucleus. Okay, so think of it like this. If I were taking, and I'll just use a gun and a bullet as an example, if I'm shooting it into a target, it should go through every single time, right? And so usually when you have a target, you have it sitting on something. And so you're shooting it, let's say you were taking it, let's say not paper, let's just take a gun, you're going to shoot into a wall. Shoo, 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 goes through the wall every time. Why? That's easy. But all of a sudden, boom, whee! It had to hit something. What's the only thing in the wall that could make it bounce back? And that'd be maybe a pipe. It hit a pipe and it ricocheted, right? He said, well, the atom's mostly empty space, but there must be a dense center called the atom. And you put all those positive parts in there. And he said, all those positive parts I'm going to call the proton. And he said, but that proton is all in the middle. And he said, these electrons, remember who's given credit for that was Thomson, electrons rotate around the nucleus. He said, I'm going to call it the planetary model. And that makes sense because that's what the planets do, right? Rutherford does more than anybody else with the atom. And he said, I don't see this is right. He said, I see the nucleus, and then the electrons are spinning around like the planets going around the sun. Now, this is not a really good picture. This is how you drew it in middle school, because this is a flat two-dimensional picture, but basically the idea of the nucleus and the electrons are going all the way around it. So imagine if this dot right here, a student at the back of my room, which is about 25 feet from me, if I told them, I want you to make a spitball with a piece of paper and I want you to throw it, you get one shot. What are the chances he's going to hit that dot from 25 feet in the back of my room? Probably 0%, right? He might hit here, 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 here. He may not even make it all the way here, but he's going to hit all these places, right? And that's what Rutherford thought this gold foil was like. When he was shooting these alpha particles through there, he said most of them are flying right through, because in reality, an atom doesn't really, he said it's rotating, okay? So in reality, the atom's really going to look like this, a nucleus. And the electrons are spinning around it. And so most times they miss. The only times they would bounce back is if one hit right on the nucleus and bounced back. And how often would that happen? Well, from his experiment, very little. He said the atom's mostly empty space. There's a dense center in the atom called the nucleus, and that's where all those protons are. And he said electrons are spinning around it like the planets around the sun. And when he published all of his information, science was like, that's the only thing that explains what we see in the atom. So J.J. Thomson's idea of plum pudding theory wasn't right anymore. And they came up now with the planetary model. The planetary model is really more of a two-dimensional, and we're going to move forward a little bit from that. But we end up having this planetary model. Wow, that's come a long way from guessing, hasn't it? And Dalton, who had tiny, hard, solid spheres, boy, it changed a lot from their experiments. Okay? And so Becquerel's work with radioactivity, if he hadn't discovered radioactivity, Rutherford couldn't do his work. If Crook hadn't done his work, J.J. Thomson couldn't have used the cathode ray tube. Okay? Then there's this last guy named Chadwick, and here's what happens. Rutherford's a super smart guy. Okay, let me show you. Rutherford knew that if you took an element like nitrogen and you had the weight of 7 protons and 7 electrons, he did the math on a calculator, and he added it all together. He said, here's how much it should weigh. And looked on the periodic table. No, it weighed more, way more than that. Hang on, another element. If I took oxygen that I know has 8 protons and 8 electrons, add all that together, because they knew how much 1 proton and 1 electron, they did all the experiments. Everything on the periodic table always weighed more than the protons and electrons. And Rutherford said, hey, there must be something else in the atom. It's not positive, we already found that. It's not negative, we already found that. He said it must be neutral, but it has mass. Now, you and I know it is the neutron. It would take them multiple years to prove the existence of the neutron. Rutherford knew mathematically there had to be neutrons, but it wasn't for multiple years until a guy by the name of Chadwick. He's the guy that discovered the neutron. Now we have all the parts of the atom. Okay? So starting at the front very quickly, the ancient Greeks were having a discussion on what makes the universe. That was the idea. Did everyone believe it? Nope. They believed this for a long time until Dalton came along. And Dalton said, with experiments, I think atoms are tiny solid spheres. You can't break them up. There's nothing inside. Well, he was wrong. And he was wrong when Thomson came along with the cathode ray tube that Crook had made, changed it, proved the existence that everything had a negative part. When the negative part came out, you had the plum pudding theory, which Rutherford proved wrong from his gold foil experiment. He said the atom is mostly empty space, dense center called the nucleus. That's where the protons are. Electrons rotate around it, called the planetary model. And the idea of the atom now starts looking like this. But also he knew that it didn't weigh enough. It took him multiple years until James Chadwick came along and proved that. Now, there's some problems with Rutherford's model of the atom. And these are all the guys in the very end. I want to make sure you catch this. Here's what they decided so far. Rutherford's right. Everybody knew that the planetary model was probably right. Protons are in the nucleus, right? And let's just have an electron right here. We'll just put 1. What's the charge of the nucleus? Well, if it's protons in there, that means the nucleus is positive. And the electron is negative. Positives and negatives do what? They attract. And so what should happen is, if I draw it on there really well, what should happen is, if I have this electron out here, it should rotate and should be slowly pulled into the nucleus because they're attracted till it crashes into the nucleus. But does that happen? If that happened, the atom would completely fall apart. No. Atoms don't collapse. Now, they didn't know why yet. That's a problem with Rutherford's model. Everyone believed that he was right. He got the Nobel Prize for all of his work, proved the protons, the nucleus, and all that kind of stuff with great experimental value and data, but they couldn't explain why. It's going to be another guy coming along, Niels Bohr. We'll talk about him in a couple days. That guy right there will prove why this doesn't happen. But for right now, we leave it with a mystery. Atoms don't collapse. We don't know why, but we'll solve it pretty quick. These are the atomic models that started out the idea of the atom.